All right, here we're going to look at symmetry in section 3.1. And we all probably remember the idea that we had the letter A had a line of symmetry that we could draw down the middle, because what happened again was when I folded each of those points over that line, they landed on another point on the other side. We're going to deal with something similar to that, and we're going to deal with it in terms of functions. So we're going to start out with the idea about symmetry about a point. And how we can deal with symmetry about a point is if I take a point and I want to reflect it over that point. And one of the things that we want to do is start out by looking at, okay, how far is it to that point? So we draw a line between the 2 points, and we continue that line through until we get a point that's equidistant from the point that we're reflecting over. So what it ends up becoming is that point is our midpoint of that line. So if I picked another point, distance, same distance, we have our midpoint. Because one of the symmetries that we'll look at with our functions is symmetry with respect to the origin. Okay, and so what we want to do is we want to be able to reflect things across the origin. So again, same idea. If I take a point here and I look at that distance to my origin, okay, what we could do is also go with the Pythagorean theorem and look at, you know, your x change and your y change here and use those values to get to your reflected point. Okay, and we could do that. And now what we want to look at is if I have a function, is that function going to be symmetric with respect to the origin? And so what we need to check is, okay, this point right here, do I have another point the same distance away from it? We can look at these things on the calculator, okay, or we can use an algebraic rule. And that algebraic rule says that if x, y is a point on my graph, if it's symmetric with respect to the origin, then the point opposite of x, opposite y, will also be a point on that graph. And so what we do is we take our function, in this case we're going to use x times y equals 4. I'm going to substitute the opposite of x, opposite of y into this equation. So my x value is the opposite of x, my y value is the opposite of y, and that's going to be equal to 4. Okay. If I simplify this down, negative times negative becomes a positive, xy equals 4. If I can get back to what I started with, okay, get back to my original, then that symmetry holds. Okay. So this function would be symmetric with respect to the origin. Now, if you think about the graph, it's a rational function. I could solve it for y, and it would be y equals 4 over x. And so because of that, what we would have is the vertical asymptote, the horizontal asymptote. You could plot some points. If I use x equals 1, I'm up here at 4. Okay, 2. And when I use 4, I'm going to be at 1. I'm going to use those 3 points. And if I think about going the other direction, okay, 4 divided by negative 1 takes me down to negative 4. 4 divided by negative 2 is at negative 2. 4 divided by negative 4 is 1. If we go to that idea again, okay, do I have a point that's the same distance on the same line away from that origin? Okay. And that's what creates our symmetry. And all three of these points that I plotted have that symmetry. Now a graph again would come like this. Okay, so keep that graph in mind as we go on to some of these next types of symmetry. When we move on to line symmetry, it's similar fashion. It's that if I'm going to reflect a point across this line, okay, what I have to do is look at how far we are from that line. And when we do that, we're talking about that perpendicular distance. And again, what I'm going to do is keep that line going and then find that same distance from the line as the reflected point. Okay, so if I chose another point, perpendicular, continue your line through, make sure they're the same distance. So we're going to have 4 types of line symmetry we're going to worry about. One's going to be symmetry with respect to the x-axis. And so think about this situation. If I'm doing it here, okay, I have a point there. Since it's a horizontal line, I know it's my vertical line, so I'm going to go find the perpendicular distance. There's 2, so I'm going to follow it through to 2. Think about my ordered pairs. At this point right now, we're at negative 9, 2. At this point, we're at negative 9, negative 2. If I do the same thing up here, okay, if I take this point at 1, 7, I figure out my distance to the line. Well, that's 7. I continue it through another 7. Now that point is 1, negative 7. Look at my ordered pairs. Look how my ordered pairs changed. In both cases, my x values, stayed the same. Okay. But my y values are now simply the opposite. And that's why algebraically what we'll do is we'll look at, in the original it's y, in my transfer, my reflected point, it's going to be the opposite of y. So when we do the same idea here, I'm going to take this equation xy equals 4. Now think back to this graph of that function. Obviously you can see that when I have this piece, if it were to be reflected, it should be up there. Okay, so we shouldn't have symmetry with respect to the line or the x-axis, but we're going to go show it algebraically now because we're not going to always graph these. So I'm going to plug in for x, my x, and plug in for y the opposite of y. And when I simplify that out, okay, it's not the original, therefore not symmetric. Okay. In some graphs, yeah, it's easy to see that they're not symmetric with respect to whichever of these that we're looking at, but we don't want to always graph them. Okay. And some of them we won't know exactly what they look like. Okay. If we go to y-axis, same idea, and I'm just going to do it quickly here, is I got a point here at negative 1, 3. Okay. If I go perpendicular to the y-axis, same distance across, what you should notice in this case is that my x value is the one that changed. So when I go and try and test for symmetry with respect to the y-axis here, I'm plugging in this ordered pair, opposite of x, y, simplify, not the same, not symmetric. Third type of line symmetry we look at is the line y equals x. Again, remember it's y equals 1x plus 0, so that's why we have the y-intercept at 0, up 1 over 1. Okay, so now when I think about that function that we just got done dealing with, I'm going to go with the point 1, 4. Okay, and then I'm going to go to the point 4, 1. Okay, and also the point 2, 2. Notice what happened. All that changed was that my ordered pairs now have flipped. My x became y, my y became the x. And so that's how we're going to check for symmetry with respect to the line y equals x. So I'm going to replace my x, my x with that x coordinate, y, my y with this y coordinate, x. Commutative property says I can switch this around. Therefore, I got the same thing. Therefore, we have symmetry with respect to the line y equals the opposite of x. Sorry, take that back. Y equals x. All right, y equals the opposite of x here now. Same idea. Negative 1 is my slope. Y-intercept is 0. Okay, I'm going to go to these points again I've been using. 1, 4, 2, 2, 4, 1. Okay, over here we had points at negative 1, negative 4. Okay. Over here we had negative 2, negative 2, and we had negative 4, negative 1. Okay. Now we talk about symmetry again, and when we do that, remember we're trying to go to the line, perpendicular, and follow it through. That one got reflected to there. to the line and through. 4, 1 reflected to there. So when I look at my ordered pairs in this situation, okay, the 1 became a -4, the 4 became a -1. So what happened was my x became what the opposite of y was, my y became what the opposite of x was. So same idea, substitute it in. My x value now is the opposite of y, my y value now is the opposite of x, and again, because I got back to my original, we have symmetry. All right, if we run into an even function, it's because it is symmetric with respect to the y-axis. Okay, we'll talk about even functions. Don't get hung up on looking at exponents. Some people do that. What we want to do is check for symmetry with respect to the y-axis, which again tells me if the x, y is on my graph, then I should also see the opposite of xy. So all we're going to do is test it to see if it's symmetric with respect to the y-axis. Odd function, symmetric with respect to the origin. So same thing, that's what we'll check. If anybody asks, is it an odd or an even function? Okay, I'm going to say it is if it has symmetry with respect to the origin, which again is opposite of x, opposite of y. All right, so just quickly, here's my new function, x plus y squared equals 1. Now I want to check for symmetry with all these. So all I'm going to do is substitute in, see if I can make them look like the original. Okay, so with the origin, opposite of x is my x, plus opposite of y is my y, squared equals 1. Now, when I deal with this opposite of y, okay, I'm going to actually think about it as a -1y squared. And when we square a product, okay, I square both the number piece, which becomes +1, and the variable. I did not get back to my original, therefore I do not have symmetry with respect to the origin. X-axis. X plus my y, this time is the opposite of y, squared equals 1. Again, that idea with the squared. It becomes a +1y squared, so I do have symmetry with respect to the x-axis. Okay. With the y-axis, opposite of x plus y squared equals 1. Quick and easy to see no. I can't make that look like the original. Okay. Y equals x. My x this time is y. My y is x squared. Okay. And if I were to try and put this back into my original form, what you're going to see to get it to be an x, I have to take the square root, but then I have to take the square root here as well. So you're not going to be able to get those back. When your two variables have opposite exponents, or different exponents, I should say, you're not going to have symmetry. Okay? And the same thing's going to happen here. Even after I square, I'm not going to be able to change my y to a y squared and my x squared to an x. So we don't have symmetry there. All right. Good luck with this assignment.